Let's continue our discussion on subspaces. So let's say that V is a vector space. And let's say that S is a subspace. So if S is a subspace of V, we have this interesting property. It says that the zero vector belongs to S. So whenever you have a subspace, you always have the zero vector in that subspace. How can we show this? Well, if X belongs to your subspace, remember your subspace is non-empty, then alpha times X belongs to your subspace. And if alpha is equal to -1, you can see that negative X belongs to your subspace. And a subspace is closed under addition. So this sum, X plus negative X, that belongs to your subspace. So you see that 0 belongs to your subspace. Now, why is this important? I mean, it is interesting that the zero vector is always there. But this can actually help us prove if something is a subspace or not. So what I have is that S is a subspace implies 0 belongs to that subspace. So if you can show that 0 is not in a set, then this will tell you that S is not a subspace. This is the contrapositive of this statement. So the opposite of this implies the opposite of this. Now, if 0 is in your set, that does not mean that S is a subspace. It's only if 0 is not an S. So let's look back at some of the examples we did in the previous video. So I'm going to scroll up to the beginning. Let's see. Like this one here. This was the first example we did. We had that V is equal to R2 and S is equal to these vectors where x1 is equal to 5x2. Now we showed that this was a subspace. And you can see that the vector 0, 0 passes this rule. If you plug in 0 here, you get 0. But just because the 0 vector is in here, that doesn't make it a subspace. You have to still check that it's closed under addition and scalar multiplication. So it's not enough to just say, oh, the 0 vector is in there, so it's a subspace. You can't do that. But where it is helpful, we had one example that was not a subspace. I'm going to scroll down. This one right here. We said that V is the set of 2 by 2 matrices, and S is the set of all matrices that take this form, where we fix this 1 here, and A, B, and C can change. We said that this is not a subspace, and how we showed it was we said that if we add 2 vectors in that set, we get something that's not in the set. We got a 2 here instead of a 1, and that's perfectly fine. You can show it just like this, but something else you can do is you can show that 0 does not belong to this set here. So this 0 vector, this 2 by 2 0 vector, does not belong here because we don't have a 1 fixed right here. So if you can just say, oh, the 0 vector does not belong, then this is not a subspace. Okay? So that's just a quicker way to show something is not a subspace, by showing that the 0 vector is not there. So let me scroll back down. But again, I want to be very clear about this. If 0 belongs to S, that does not mean S is a subspace. Okay? So this should be just something you checked to see really quickly if it's not a subspace. If it's not in there, then it's not a subspace. But if you find that 0 is in the set, then you still have to check if it's closed under scalar multiplication and vector addition. let's move on. I want to talk about an important subspace of Rn, and that's called the null space of a matrix. So suppose we have an m by n matrix. The null space, which we write like this, we denote it this way, n of A, this is equal to all solutions to A times x is equal to 0. Let me write this in set notation. The null space is a set of all x in Rn such that A times x is equal to 0. We're looking for column vectors because, remember, this is an A m by n matrix, and this column vector is going to be n by 1 in order for this and this to cancel, and what we're going to be left with is a 0 matrix that's m by 1. Now this is the set of all solutions in Rn. Okay, so our column vectors are coming from Rn. Let's show that the null space is a subspace of Rn. So A is a n by n matrix. And we said that the null space is all the vectors x and Rn such that A times x is the m by 1 0 vector. How can we show it's a subspace? First, we have to ask ourselves, is this actually a subset of Rn? Well, by definition it is. And is it non-empty? That answer is yes, because the 0 vector is always a solution to a matrix times x is equal to 0. So it's non-empty. So it's a non-empty subset of Rn since the 0 n by 1 vector satisfies A times 0 is equal to 0. Okay, the other two properties we have to check is if scalar multiplication and vector addition, if we add two vectors together, that is in the null space, and if we multiply scalar by a vector, that's in the null space as well. Okay, so let's check vector addition. So if x and y belong to the null space, does x plus y belong to the null space? And the answer is yes. Let's see it. Get some more space here. So if x and y belong to the null space, that means A times x is equal to 0 and A times y is equal to 0. We want to see if this belongs to the null space. So if we apply A to x plus y, well, now we use properties of matrices. We know that this is the same thing as A times x plus A times y. But A times x is 0 and A times y is 0, so we get 0. So we can see that A applied to x plus y is equal to 0. So this is a solution to A times a vector is equal to 0. So this tells me that x plus y belongs to the null space. Now let's check and see if the null space is closed under scalar multiplication. If alpha is a scalar and x belongs to the null space, does alpha times x belong to the null space? Well, we're going to apply A to, I'm going to do this in black, apply A to alpha times x. Now this is a scalar, this is a matrix, this is a matrix. We can pull this scalar out. This is the same thing as alpha times A times X. But A times X, because X is in the null space, this is equal to 0. And any number times 0 is 0. So you can see that when we apply A to alpha times X, we get 0. So this is a solution to this A times a vector, column vector is equal to 0. So we see that alpha times X belongs to the null space. And so the null space is a subspace of Rn. Let's work on an actual example of finding the null space of a matrix. So maybe this will help you understand null spaces better. So this is number 4b from your book in section 3.2. The example says, determine the null space of this 2x4 matrix. 2 rows, 4 columns. So we want to find the null space, which is the set of all vectors. Now we need to figure out what space we're working with. This is a 2x4 matrix, so it should be all vectors in R4 that satisfy A times X is equal to 0. And I also want to ask you, what size is this 0 matrix? Well, we're going to take a 2x4 matrix and multiply it with a 4x1 matrix. So we'll get a 2x1 matrix. So this is going to be 2x1. Okay, so what I'm going to do, first I'm going to write this out. This is 1, 2, -3, -1, -2, -4, 6, 3. This is A. And then we're multiplying it by x1, x2, x3, x4. And I want to get the 0 2x1 matrix. So I'm looking for the solutions that satisfy this, that A times this column vector is this. So I need to find x1, x2, x3, and x4. Well, if you multiply these matrices, you get a system. You get that x1 plus 2x2 minus 3x3 minus x4 is 0, and negative 2x1 minus 4x2, and so on, that's equal to 0. So all you have to do is put this in an augmented matrix and get this augmented matrix in reduced row echelon form. Okay, so how can we do that? Well, I'm going to leave this top row alone, and I'm going to multiply the first row by 2 and add it to the second row. Oops. So we'll get 2, 4, -6, -2, 0. And I'll be left with 0, 0, 0, 1, 0. And then from here, I want it in reduced row echelon form, so I just need to zero out this one here. So I'm going to take row 2 plus row 1. 1, 2, -3, 0, 0, 0, 0, 0, 1, 0. And now let's relate this back to our system. This says that x1 plus 2x2 minus 3x3 is 0, and x4 is 0. So we know what x4 is. And then we're going to solve for this pivot here by moving everything on to the right. So we get x1 is negative 2x2 plus 3x3, and x4 is 0. So one way to write the null space in set notation is that it's the set of vectors that look like this. We put 0 in for x4. We put negative 2, so x2 and x3 are free variables. You can say that x2, let's say x2 is r, and x3 is s. We can choose whatever we want for x2 and x3. However, whatever we choose for these will determine what x1 is, and x4 is always going to be 0. So the null space is the set of vectors that look like negative 2r plus 3s, x2 is r, x3 is s, and x4 is 0. Just by following what I have here, such that r and s are real numbers. You can check this. So vectors in the null space, if you let r equal 1, and let's say we let s equal 2, then we'll have negative 2 times 1 plus 3 times 2, 1, 2, 0. This is negative 2 plus 6, it's 4, 1, 2, 0. This vector is in the null space. So what should happen is, if I take my matrix A and I multiply it by 4, 1, 2, 0, I should get 0, 0. Double check that. That's a good way to make sure you got the right answer. If something goes wrong and you get a number other than 0 here, you probably messed up with getting this matrix into reduced row echelon form. Alright, so we have described the null space.